Welcome to DAR Tutors for online and home tuition. In this video, we'll explore the fascinating world of Voronoi diagrams. We'll cover several key concepts and problem-solving techniques relevant to the IB mathematics applications and interpretation higher-level curriculum. By the end of this session, you will be able to construct and interpret Voronoi diagrams, solve problems involving nearest neighbor interpolation, find the largest empty circle, and tackle IB-style questions on these topics. Let's begin by introducing the core idea of a Voronoi diagram through a practical problem. Imagine a city with several fire stations. When a fire breaks out, it's crucial to dispatch the nearest station to minimize response time. Here's a map showing 4 fire stations labeled A, B, C, and D. Our goal is to determine which station is closest to any point in the city. Let's consider a specific location, say at coordinates 6, 3. Which fire station is closest? We could use the distance formula to find the distance to each station. However, this is time-consuming if we need to do it from many points. What if we want to know, visually, the entire region of the city that's closest to a particular station? This is where Voronoi diagrams become incredibly useful. A Voronoi diagram partitions a plane with a set of points, called sites, into regions. For each site, its Voronoi cell consists of all points in the plane that are closer to that site than to any other site. Think about it like this. Every house in the city belongs to one fire station's catchment area. This catchment area is a Voronoi cell. Here's the Voronoi diagram for our fire stations. We can see 4 distinct cells, each colored differently and containing one station. Any point inside the yellow region is closest to station B. Any point inside the green region is closest to station C. Now let's recap our learning objectives. We've introduced Voronoi diagrams as a way to partition space based on proximity to a set of sites. You should now be able to explain their purpose and recognize their basic structure. In the next section, we'll dive into how to build these diagrams. Let's define the key components of any Voronoi diagram. First, we have sites. These are the original points, like our fire stations, that define the diagram. Second, there are cells, or regions. Each site is surrounded by a cell that contains all points closest to that site. Third, we have edges. These are the lines that form the boundaries between cells. A key property is that any point lying on an edge is equidistant from the 2 sites whose cells are separated by that edge. For example, if you stand on an edge between cell A and cell B, you are the same distance from site A and site B. Fourth, and finally, we have vertices. These are the points where 3 or more edges meet. A vertex is equidistant from all the sites whose cells share that vertex. So a vertex where edges from sites A, B, and C meet is equally close to A, B, and C. Let's look at this diagram with 5 sites. Point A is a site. The blue edge separates the cell of site B from the cell of site C. Any point on this edge is equidistant from B and C. The red vertex is a vertex where the cells of C, D, and E meet. This vertex is equidistant from C, D, and E. Here's a quick exercise. Take a moment to think about this diagram. How many cells does it contain? How many vertices? And which site is closest to the point, as chapter 1, 2? If you said 4 cells, that's correct, 1 for each site. 3 vertices and the point, 1 and 2, is closest to sites C and D because it lies on the edge between their cells. Excellent. To recap, we've broken down Voronoi diagrams into their key parts. You should now be able to identify sites, cells, edges, and vertices, and understand their fundamental properties, such as points on an edge being equidistant from 2 sites, and a vertex being equidistant from 3. Now that we understand the anatomy of a Voronoi diagram, let's learn how to construct one. This is a fundamental skill in this topic. The key mathematical tool we use for construction is the perpendicular bisector. Recall that the perpendicular bisector of a line segment AB is a line that passes through the midpoint of AB and is perpendicular to AB. The crucial property for us is that every single point on this line is equidistant from point A and point B. Conversely, any point that is equidistant from A and B must lie on this line. Therefore, the edges of a Voronoi diagram are simply segments of these perpendicular bisectors. For 2 sites, A and B, the Voronoi diagram is just a single straight line. the perpendicular bisector of the segment AB. One side of the line is closer to A, the other is closer to B. For three sites, A, B, and C, we start by drawing the perpendicular bisector for every pair of sites, PBAB, PBBC, and PBAC. These three lines will intersect at a single point, a vertex, which is equidistant from all three sites. The actual edges of the Voronoi diagram are the portions of these bisectors that are closest to their respective sites. We make these parts solid and the rest dashed. So, to recap, the key to construction is finding perpendicular bisectors. Each edge of a Voronoi diagram is part of the perpendicular bisector of the two sites it separates. The intersections of these bisectors give us the vertices of the diagram. Let's work through an example to see this construction method in action. This is the main skill you'll need to develop. Our objective is to construct the Voronoi diagram for three sites, A at -5, 2, B at 3, -4, and C at -3, -2. First, we plot the sites on a coordinate plane. Next, we calculate the perpendicular bisector for each pair of sites. Let's start with sites A and B. We find the midpoint of the segment from A to B using the midpoint formula, which gives us m sub AB at -1, -1. Then we find the gradient of the line from A to B. The change in y over the change in x gives us -6/8, which is -3/4. The gradient of the perpendicular bisector will be the negative reciprocal of this, which is 4/3. So, the perpendicular bisector between A and B passes through -1, -1, and has a gradient of 4/3. We can repeat this process for the other two pairs. For A and C, we find the midpoint at -4, 0, and the gradient of the bisector is 1/2. For B and C, the midpoint is 0, -3, and the gradient is 3. Now we draw all three of these perpendicular bisectors. Notice they all meet at a single vertex. The parts that form the actual boundaries between the cells are made solid. And there you have it, the Voronoi diagram for our three sites. Each edge is a segment of a perpendicular bisector, and they meet at a vertex that is equidistant from A, B, and C. To recap, we've now seen how to construct a Voronoi diagram by calculating the midpoint and gradient for each pair of sites. This determines the equations of the perpendicular bisectors, which are the basis for the diagram's edges. So we can draw a Voronoi diagram from scratch. But what happens if we're given a diagram that's incomplete, perhaps missing a site? The objective of this section is to deduce the coordinates of a missing site given its partial Voronoi diagram. Consider this diagram. We have sites A, B, and C, but there's an empty cell. We'll call the missing site X. Remember the key properties of edges and vertices. The edges bordering the empty cell are the perpendicular bisectors between the missing site X and the known sites A, B, and D. For example, the bottom edge is PBDX, and the top edge is PBAX. The vertex where these meet, let's call it V, must be equidistant from AD and the missing site X. A very common and useful trick is to observe the gradients of these edges. If an edge is perfectly horizontal or vertical, it tells us something special about the sites. Notice the top edge, PBAX, is horizontal. This implies the line segment connecting A and X must be vertical. Since A is at 3, 4, and AX is vertical, X must also have an X coordinate of 3. Now let's look at the bottom edge, PBDX. Its gradient appears to be 1/3. A perpendicular line would have a gradient of 3. We can now use this information to find X. We know its X coordinate is 3, and we know it lies on a line with gradient 3 that passes through site D. Using the point-slope form, the equation of the line dx is y. Sarsh 3 equals R3 x 2, which simplifies to y equals 3x 9. Since the x-coordinate of x is 3, we substitute to get y equals 3 or 3, 9 equals 0. Therefore, the site x is at 3, 0. Alternatively, you could visually trace a vertical line from A and a line with gradient 3 from D and see where they intersect. They intersect at 3, 0. To recap, finding a missing site involves using the properties of its Voronoi cell edges. Looking for horizontal or vertical edges can be a great shortcut, and then using perpendicular gradient and the site's coordinates will lead you to the missing site. We've now reached the 10-minute mark. Before we continue, I want to take a moment to thank you for watching. If you're looking for personalized expert guidance for your IB A-level or IGCSE studies, I invite you to contact DAR Tutors. Our experienced tutors provide tailored support to help students achieve their academic goals. Whether you need help with a specific concept or want to build a strong foundation across the curriculum, DAR Tutors is here to help. Get in touch today to see how we can assist you on your educational journey. Now let's get back to our lesson on Voronoi diagrams. So far, we've constructed diagrams from scratch and found missing sites. Now, what if we have an existing diagram and need to add a new site? Our goal is to understand and apply the procedure for updating a Voronoi diagram when a new site is introduced. The process is step by step and depends on the location of the new site. Let's use an example. We have sites A, B, and C. A new site, D, is being built. Notice that currently, the location for D lies within the cell of B. Step 1. Since D is in B's cell, we construct the perpendicular bisector between them, PBD. We draw it starting from D. Where it intersects the existing edges of cell B, we create new vertices. In our example, PBBD intersects the edge PBAB at a vertex we can call V. Step 2. This new vertex 5 is adjacent to cells A, B, and D. We must check which other existing cells are adjacent to these new vertices. For each, we construct a perpendicular bisector with D. Our new vertex 5 is equidistant from A, B, and D. It's a new vertex of our diagram. We must now draw the new edge PBAD from this vertex. We continue this process until the new cell for D is completely enclosed and no new vertices are created. Step 3. Finally, we remove any parts of the old Voronoi diagram that are now inside the new cell D. For instance, the section of PBAB that is now closer to D than to B is removed. Notice that cell C was not affected. This is because it was far enough away that its region was not taken over by the new site D. Let's summarize the procedure. First, find the cell containing the new site and draw its perpendicular bisector with that site. Second, extend bisectors from new vertices until the new cell is enclosed. Third, delete the obsolete parts of the old diagram. You can redraw the entire diagram if that's easier. Recap. Adding a site updates the diagram. We've learned a 3-step process to incorporate a new site cell by drawing a series of perpendicular bisectors and removing obsolete boundaries. You can now trace this process in a diagram. Now let's see how Voronoi diagrams are applied in a technique called nearest neighbor interpolation. The objective here is to use a Voronoi diagram to estimate a value at an unknown location based on nearby measurements. Imagine we've measured rainfall at several locations, A, B, and C. Now we want to estimate the rainfall at any other point in the city. Interpolation is the general process of estimating values between known data points. Nearest neighbor interpolation is the simplest form. Nearest neighbor interpolation states that the value at an unknown point is the same as the value at the closest known point. Since a Voronoi cell defines the region closest to a site, the value at any point within a cell will be the value associated with the site of that cell. Let's use our rainfall example. Here are the measurements. 12 mm at A, 7 mm at B, and 15 mm at C. Now here's the corresponding Voronoi diagram. The plane is divided into 3 regions, cell A, cell B, and cell C. First, let's estimate the rainfall at the point R4, 1. We find this point on our diagram. Notice it lies inside the blue region, which is cell C. This means that site C is the nearest neighbor to 4, 1. So, our estimate for the rainfall at 4, 1 is the same as the rainfall at site C, which is 15 millimeters. What about the point 1, 1? When we plot this point, we find it's a Voronoi vertex. A vertex is equally closest to all sites whose cells meet there. In the case of a vertex or an edge, the convention for nearest neighbor interpolation is to take the average of the values from all equidistant sites. This vertex is equidistant from sites A, B, and C. So we calculate the average of their rainfall values. Our 12 plus 7 plus 15 divided by 3, which is 34.3, or approximately 11.3 millimeters. To recap, nearest neighbor interpolation is a straightforward way to estimate values using a Voronoi diagram. We identify the cell an unknown point is in and assign it the value of that cell's site. If the point is on an edge or vertex, we average the values of the equidistant sites. Our final topic in Voronoi diagrams is the largest empty circle problem. The objective is to find the center and radius of the largest circle that doesn't contain any sites, but is itself contained within the convex hull of the sites. This might sound a bit abstract, but it has practical applications. It's sometimes called the toxic waste dump problem. Imagine a city with several towns. You need to build a new facility, like a rubbish dump, but you want to place it as far as possible from the nearest town. This is equivalent to finding the largest empty circle whose center is the optimal location, and whose radius is the maximum possible distance to the nearest town. The convex hull is just the smallest convex polygon that contains all the sites. The center of the largest empty circle must lie within this hull. For the problems we'll consider, the key insight is this. The center of the largest empty circle will always be a Voronoi vertex. The vertex we're looking for is the one that is the greatest distance from its equidistant sites. Let's work through an example. Here we have the sites A2-1, B-1-4, C2-3, and D2-3. The diagram has been drawn for us, and its vertices are labeled as V1 at Shur2 and V2 at 1 thou. First, let's analyze vertex V1. It's formed by the cells of sites A, B, and C, meaning it is equidistant from these three sites. We calculate the distance from V1 to A using the distance formula. This gives us the square root of 5 units. This distance is the radius of the circle that would have its center at V1. Next, let's look at vertex V2. It's equidistant from sites A, C, and D. We calculate the distance from V2 to A. This gives us the square root of 10 units. We compare the two radii we found. Since the square root of 10 is greater than the square root of 5, the circle centered at V2 is the largest. Therefore, the largest empty circle has its center at the Voronoi vertex V210 and a radius of the square root of 10 units. To summarize, to find the largest empty circle, you must find all the vertices of the Voronoi diagram. Then calculate the distance from each vertex to its equidistant sites, as this distance is the radius. The vertex that yields the largest radius is your answer. Now that we've covered the main topics, let's test your understanding with some IB-style practice questions. Question 1 will reinforce your ability to interpret a Voronoi diagram. Here's the problem. You are given a Voronoi diagram for 3 sites, A, B, and C. The central vertex is V. The first part asks for the number of cells, edges, and vertices. Looking at the diagram, we can see it contains 3 cells, one for each site. The edges are the boundaries between cells, and there are also 3 edges. Finally, all 3 edges meet at a single central vertex. The second part asks which site is closest to the point Q with coordinates 1, 0. Plotting Q at 1, 0, we can see it lies directly on an edge of the diagram. Remember that points on an edge are equally closest to the 2 sites that share that boundary. This edge separates the cells of sites A and C. So, point Q is equally closest to both site A and site C. Due to a slight ambiguity between the diagram and a point's coordinates, we will assume, for the sake of demonstrating the concept, that point Q is intended to be on an edge. The key takeaway is, if a point is on an edge, it is equidistant from the 2 sites of the cells it divides. If it's in a cell, it's closest to that cell's site. Our next practice question focuses on construction, a core skill for this topic. Here's the problem. You need to construct a Voronoi diagram for sites A2, 5, and B4, 3, and then find the equation of the resulting Voronoi edge. As we learned, the Voronoi diagram for 2 sites is simply the perpendicular bisector of the segment connecting them. Our first step is to plot the 2 sites, A2, 5, and B4, 3, on a coordinate plane. Next, we find the equation of the perpendicular bisector in 2 steps. Step 1. Find the midpoint. Using the midpoint formula, the midpoint of AB is at 1, 4. This point must lie on our bisector. Step 2. Find the gradient. First, the gradient of the line AB is 1, 3. The gradient of the perpendicular bisector, therefore, is the negative reciprocal, which is 3. So, the edge we're looking for is a line with gradient 3 passing through the point 1, 4. Using the point slope form, y equal y1 equal mx x1, we get y, 4x3 x1, which simplifies to y equals 3x plus 1. This line, y equals 3x plus 1, is the Voronoi edge. Any point on this line is equidistant from sites A and B, Any point to the left of the line is closer to A, and any point to the right is closer to B. We can draw this line on our graph. To verify this, we are asked to check if the point, 2, 5, is on the edge and equidistant from A and B. To check if it's on the edge, we substitute its coordinates into our equation. 5, x3 plus 2 plus 1, which simplifies to 5 equal 5. The equation holds, so it is on the edge. To check for equidistance, we calculate the distance to A and B. Both distances are the square root of 34, confirming it is equidistant. The process of finding the perpendicular bisector is robust and reliable. Let's move on to a problem involving adding a site to an existing diagram. In this problem, we have an existing Voronoi diagram for sites A, B, and C. We need to redraw it with a new site D at ∈ 0. The first step is always to identify the cell where the new site lies. The original diagram had its central vertex at the origin, 0, 0. Plotting D at pointer 2, 0 shows it is clearly in the cell belonging to site C, which is the bottom left quadrant. According to our rules, since D is in C's cell, we construct the perpendicular bisector PBCD. The midpoint of CD is 1.5, 1, and the gradient is 1. So the perpendicular bisector has a gradient of 1. Its equation is y equals x plus 0.5. We draw a segment of y equals x plus 0.5 starting from D. It intersects the old edge PBAC at a new vertex. Let's call it V1. This vertex is equidistant from AC and D. Next, we draw the new edge PBAD from vertex V1. The bisector of AD is the vertical line x equals 1. This line is PBAD. This edge now completes cell D and meets another old edge, PBBA, at a new vertex V2. This vertex is equidistant from BA and D. So we have a new vertex V1, formed by the intersection of PBAC and PBDC. We then construct PBAD from V1 until it meets the edge PBAB at a new vertex V2. Finally, we remove the obsolete parts of the old diagram that are now inside the new cell D. The resulting diagram shows the new cell for D and the affected cells of A and C. Cell B was far enough away that it was not affected. Our fourth practice question combines construction with the largest empty circle problem. The problem asks for the center and radius of the largest empty circle for 3 sites, A or 5, 0, B1, 6, and C7, 4. The first step is to construct the Voronoi diagram, as we did in question 2. We plot the sites and find the perpendicular bisectors. After careful calculation, you'll find they all intersect at a single vertex V at coordinates 1, 2. So the vertex of our diagram is at 1, 2. Since this is the only vertex, it must be the center of the largest empty circle. Remember, the radius of this circle is the distance from the center V to any of the equidistant sites, A, B, or C. We can calculate this distance using the distance formula for V and site A. Plugging in the coordinates, we find the distance is 10 units. You could verify this by calculating the distance to B or C. The result would be the same. Therefore, the largest empty circle for these sites is centered at 1, 2, and has a radius of the square root of 40 units. This problem illustrates the crucial connection between the geometry of the Voronoi diagram and the largest empty circle. The vertex acts as the central point for the largest area of the plane that is far from all sites. For our final practice question, we'll analyze a pre-drawn diagram to answer several questions, which is a common style in the IB. Here we have a diagram showing police stations, and our task is to find the closest station to a specific point, determine the coordinates of a vertex, and solve a largest empty circle type of problem. First, find the station closest to R3. Looking at the diagram, the point 3, 3 falls squarely within cell D. Therefore, the closest station is D. Second, find the coordinates of vertex V3. The diagram shows V3 is the vertex where the cells of B, C, and E meet. So V3 is equidistant from B, C, and E. Using the coordinates from a similar problem in the textbook, let's assume B is at 0, 7, C is at 3, 1, and E is at 4, 1. We can find V3 by finding the intersection of PBBE and PBCE. The equation of PBBE is E, we'll say 8cx plus 3.5, and PBCE is x equals 17y, 2. Substituting the second into the first and solving gives us y equal 4 and x equal 6, 7. So V3 is at 4, 6, 7, 4. Finally, we need to place a new station as far as possible from the existing ones. This is the largest empty circle problem. For this problem, the diagram provides a central vertex, V2, which appears to be the most distant from its sites. This vertex is equidistant from A, B, and E. Let's use the textbook's given vertex V2, 1 to theo. We calculate its distance to the sites it's equidistant from, A, B, and E. The distance is the square root of 26. This is the largest radius in the diagram. So the optimal placement for the new station is at the coordinates of vertex V2, which is 1, 0. The nearest station will be at a distance of the square root of 26 kilometers. The logic remains the same. The optimal location is at the Voronoi vertex that maximizes the distance to its nearest sites. Our final practice problem is a conceptual one, asking you to explain a key property of Voronoi diagrams using circles. The question is this. Let X be a site in a Voronoi diagram, and P be a point within its interior cell. If you draw a circle with center P that passes through X, why can this circle not contain any other sites? To answer this, we need to recall two fundamental definitions. First, the definition of a circle. By its very nature, every point on the circumference of a circle is equidistant from its center. In our case, the center is P, and the circle passes through X. This means the distance from P to X is the radius of the circle. Second, the definition of a Voronoi cell. Cell X contains all points that are strictly closer to site X than to any other site. Our point P is in the interior of cell X, so it satisfies this definition. Now let's put these two ideas together. Because P is in the interior of cell X, by definition, its distance to site X is less than its distance to any other site. Say Y. That is, the distance from P to X is smaller than the distance from P to Y. The circle we drew has center P and passes through X. This means its radius is precisely the distance deep out Px. Now consider any other site, Y. We know that the distance from P to Y is greater than the radius of our circle. Since Y is further from the center P than the circle's radius, site Y must lie outside the circle. This applies to every other site in the diagram. Therefore, the circle cannot contain any sites other than X itself. This property is a direct consequence of how Voronoi diagrams are defined. Recap. This question solidifies your conceptual understanding. The definition of a Voronoi cell guarantees that any point inside it is closest to that cell's site. This relationship directly prevents a circle centered in that cell and passing through its site from containing any other sites. Let's quickly review the key concepts we've covered today. First, we defined what a Voronoi diagram is. A partition of a plane into cells, each containing points closest to a given site. You should now be able to identify sites, cells, edges, and vertices. Second, we mastered the skill of constructing these diagrams. The crucial insight is that the edges are segments of perpendicular bisectors. You can now calculate the equations of these bisectors and draw the resulting diagram for a given set of sites. Third, we saw the process of adding a new site, which updates the existing diagram. This involves drawing a new set of bisectors and removing parts of the old diagram. Fourth, we looked at a practical application, nearest neighbor interpolation. This allows us to estimate values at unknown locations by finding their closest site in the Voronoi diagram. And fifth, we tackled the largest empty circle problem, which is solved by finding the Voronoi vertex that is farthest from its sites. This provides an optimal location for a facility. These concepts are fundamental in the IB Mathematics AI/HL curriculum and have wide-ranging applications in fields from science and engineering to city planning. Practice is key to mastering these techniques. Thank you for joining.